invite to the podium Professor Harry Manifavas of Ford, who is going to give us an introduction to PQC and PQC transition. Dr. Harry Manifavas is a senior research collaborator at ICS Ford, specializing in cybersecurity, cybercrime, and digital forensics. He is the author or co-author of over 60 research papers and has obtained several professional certifications. Professor Manifavas.
Hello, good morning. Okay, all right. So, PQC, post-quantum cryptography. I mentioned PQC yesterday. I guess you heard about PQC from other presenters. So we're going to go a bit deeper today. We have half an hour. So again, quantum computing is the boogeyman. We have to do something about what is coming. So a few words again about quantum computing. So quantum computers base their functionality on quantum mechanics principles like superposition, entanglement, and the no-cloning theorem. So they can do things in parallel very fast. Instead, for example, of trying one solution to a problem, they can try multiple solutions in parallel at the same time. So this gives them a big advantage. So quantum computers use qubits, like quantum bits, as the smallest unit of information. They have their own elementary instructions, like gates, logical gates to do addition or whatever we do in classical computing. And they run quantum algorithms. So quantum algorithms already know those qubit properties. They know what are the benefits, and they can take advantage of those qubit properties. So quantum computers won't deal with everything, won't solve all the problems magically. They can accelerate the solution of several problems. And in our case, some of the issues that we face in cryptography, those problems fall into this category. So they can deal with some of the cryptography problems that are difficult to solve in practice today, but they can solve those problems much faster when they become available. So one good research question is whether which are those problems that can be solved with quantum computers, right? As time goes by, we come up with more and more problems. We can also combine quantum computers with classical computers to solve problems, because we don't have enough qubits to solve the full problem. So what we can do is we can split the problem into parts. If part of the problem can be solved by a classical computer easily, then we give that part of the problem to the classical computer, and we leave the quantum computer to solve the problem that cannot be solved by the classical computer. So again, this combination makes sense, because we don't really need as big as we would like it to be a quantum computer to solve the big problem. Many applications. So with respect to cryptography, remember yesterday we said that classical cryptographic primitives like public key cryptography base their security on the difficulty of solving certain mathematical problems. These problems can be solved much faster with a quantum computer, and more specifically with something that's called a cryptographically relevant quantum computer. So what is the definition for this? It's a quantum computer of sufficient size, power, and sophistication. Size means the number of qubits that it can manipulate. The more qubits, the better. Qubits store information and can be manipulated using logical gates to run an algorithm. So the more the qubits, the better. And sophistication, that means to be able to solve complex algorithms, right? So today, there is no CRQC at the moment. In reality, it's only still theoretical, and one of the algorithms for classical public key cryptography, RSA, cannot be cracked today, but it's coming. So quantum computers do exist. They are very small. In the beginning, there were only pieces of equipment in some laboratory. But these days, we have computers in the cloud that we can use them to simulate solutions to problems. We can access those cloud platforms. This is called quantum as a service, to accustom ourselves with this new concept and this new infrastructure. Come up with our own algorithms, try them. We don't have a quantum computer in our lab, right? So this is a good opportunity for us to use such an infrastructure that is currently online. So some people are optimistic, some others are pessimistic. Some people say quantum computer good enough for solving cryptographic problems is around the corner, early 30s. Others say it's never going to happen. But in any case, we have to take some precautions, some proactive action. That's why we need to act as if they're around the corner. The time. All right. So the timeline is a bit uncertain, but still, whenever we have to deploy a crypto service, or new algorithms or new protocols, that takes a lot of time. So we have to act now. And in the meantime, obviously, we need to invest in research and development, education, and awareness. Now, there is another term called quantum advantage or supremacy. This is the time when a quantum computer will be able to solve a problem much faster than a classical computer. So Google demonstrated such an algorithm and a computer back in 2019, when the quantum computer that was hosting 53 qubits was able to solve a specific problem that it would take 10,000 years a supercomputer at that time to solve. Many people disputed the claim. They said that the algorithm that you use on the classical computer to solve the same problem is not optimal. We can come up with a better algorithm that can run even faster on a classical computer than the algorithm that you run on the quantum computer. Still, that was a big event, because they were able to solve a good enough problem on a quantum computer that hosted a good number of qubits. So as we come closer to today, Google have their own quantum roadmap, like many other companies, and they expect to, in the next few years, to have a computer that can, utilize 1,000 qubits. As we said, the more the qubits, the more sophisticated the problem it will be able to solve. This is IBM's quantum roadmap. Again, they hope to be able, before the end of this decade, to have a quantum computer utilizing around 1,000 qubits, and then try to solve problems using that machine. So sometimes, instead of putting too many qubits all together, which is like it's not as easy, they have different boards with, let's say, 100 qubits. They put everything, all those boards together, and they try to, split the problem in pieces and solve the problem this way. So there are many approaches. Quantum computer is not like the one and only, solution that is in the horizon. There are many other different solutions, right? And the way quantum computers work again, it's not like there is no only one direction. There are many different directions, right? So the term quantum computing is like a bit generic. So you have to imagine that there are many different directions and efforts going on at the moment. Europe obviously have already started their own quantum computing research effort, and they expect again to have 1,000 qubit quantum computing system before the end of this decade. So many challenges. I'm not going to go through this list. This is like a small list, I must say. There are many engineering and scientific challenges that need to be overcome. All right, that was the first part. Let's move to the second part of this presentation. Let's remember what public key cryptography is about. Public key cryptography is used mainly for two operations. One is to be able to transfer a key from place A to place B. So we usually encrypt the source session key that gets generated at place A using the public key of the recipient. We send to the recipient. The recipient uses their private key to decrypt the session key. And that session key is a symmetric key that can be used by the two parties to communicate with each other using some other algorithm. So that's a key agreement. And public key cryptography is also used for digital signatures. Every time we have to prove our identity, our intention for something, we can sign a document or some email, some piece of communication, and so on. So right now, today, if PQC algorithms, PKC algorithms are properly implemented and we use keys of the right size, they're strong enough. All right, so this is a figure demonstrating key agreement. We usually have two parties, the sender and the receiver. On the left side, the sender generates the symmetric key, encrypts the symmetric key that gets transferred to the receiver. The receiver decrypts the symmetric key. So at the end of this process, both A and B have access to a shared key, a shared secret that can be used by both to further communicate. Let's give you an example. Whenever we connect to some bank online over the internet using a browser, this negotiation takes place at the beginning, all right? So the browser and the server agree on some key, and then everything we do online, like all the packets that we exchange with all the information inside, our credit card number, purchase orders, and so on, get encrypted using that key that was negotiated at the beginning. So at the beginning, we have public key cryptography to negotiate and share a key, and then we have symmetric key cryptography to exchange information. So symmetric key cryptography cannot be used for the negotiation part. Now for the signatures function, we have some message. We calculate the hash of that message. That's like a shorter version of the message. And then we encrypt the hash with our private key. That's our signature. This is how we indicate that this came from us. With the private key that we use is not shared with anybody else. It's unique. It's connected to our identity. And this is how the recipient knows who sent the message, right? So the recipient on the other side can just verify the signature and make sure that the message that they received came from the recipient, the claimed recipient. All right. So in RSA uses long keys. I mean, in the 90s it was like 512 bits. In early this century, it was like 1024. Now the standard is around 2048 bits. Why is that? Because if you remember, computers become faster, so they're able to crack short keys. That's why you have to adapt and use longer keys. But as long as the key is long enough for the current resources that we have, that's fine. The algorithm works just fine. So in this figure, you can see the cryptanalytic effort, the length of the key that researchers were able to crack. Meaning that they were able to get the key and find the private key of the owner, right? If you find the private key, it's like you break the algorithm, you break the key. Because if you find the private key, then you can impersonate anyone. The algorithm is not good enough. And the current record is around 829 bits, which is much lower than the current standard, which is like 2048 bits. we expect a quantum computer to break RSA in seconds as long as the key is very small, right? Which is not the case. So that's not an imminent threat, but still we have to do something about it. And there was Shor in 1994, we mentioned this name yesterday again, who came up with an algorithm, right? At that time, he didn't, own a quantum computer, but still he knew how a computer would work, and was able to come up with a good algorithm that could solve this problem much faster. So according to some recent publication, to crack a 2048 RSA bit key, we need let's say 20 million qubits and 8 hours. 8 hours sounds nice. 20 million noisy qubits, that's not easy to digest. So remember the roadmap earlier? We saw that 1,000 qubits is like the target for the end of this decade. But things progress. 10 years ago, people thought that we need a billion qubits to crack RSA. Now we went down to 20 million, and obviously this number is going to be improved. We also mentioned retrospective decryption, meaning that attackers can just record traffic and try to break it, to decrypt it after a few years. So this is a big issue for some organizations or governments or other entities who don't want their data to become encrypted and become public by any means, right? Right. Let's move to symmetric key cryptography. Right? Two main types. Let's say public key cryptography, good for key sharing and digital signatures, and symmetric key cryptography, which is good for bulk encryption. Right? So whenever we need to encrypt, lots of stuff, big files, movies, whatever, we can use symmetric key cryptography. Again, symmetric key cryptography, as we know it today, is safe, is secure, as long as we use a standard algorithm and keys of the right size. There was another researcher, Grover, who in '96 came up with another algorithm that hurts a bit symmetric key cryptography, right? But not as much as source algorithm hurts public key cryptography. So a quantum computer will be able to, let's say, search through the keys. I will explain that in a bit faster. But this algorithm is not going to break symmetric key cryptography. Right? So it's a small improvement, but it's not a showstopper. Obviously, we need to be aware of the implications of this algorithm to make sure that we choose keys of the right size for symmetric key cryptography. So what are the implications of this algorithm? If we use, for example, AES, which is a standard for symmetric key cryptography, with a key size of 128-bit length, on a quantum computer, this is going to be equivalent to using AES with 64-bit size. 64-bit today is not good enough. It's a small key size. But if we use AES 256, longer key size, then that's good enough even with quantum computers, because that would be equivalent to running AES 256 divided by 2, which is 1 to 8, which is good enough. Now, what is the key? Right? The key is like a random bit string. It has to be random because we shouldn't be able to predict what the key is, so it should be random. It's a random bit string, so 128 random bits. So what is the attack exactly? One attack is to break symmetric encryption is, there are many attacks, but in this case, one attack is to try all possible keys. If the key is very short, we can try all possible keys, because if the key is short, the combinations are not that many, right? We can try one after the other. So I try key 1 with the ciphertext, try to decrypt it. Do I get something that makes sense? No. Let's try another key. Try key number 2. Let's try to decrypt the ciphertext. Do I get anything that makes sense? No. We can try all the keys, but if the key is long, the combinations are, too many. Numbers in cryptography are huge, right? And today we would need, billions and trillions of years with current technology to go through the key space, try all keys, even for AES 128. But with a quantum computer, where 128 becomes 64, 64 is feasible, right? We need to be aware of this and make the proper choices now and then. As you can see in the figure on the bottom right, public key is broken, symmetric key just the key size is halved. So as long as we double the key size, we're okay with a quantum computer. So this threat is not acceptable for public key cryptography mainly. That's why I have to take some measures, because to introduce new cryptography like QKD we discussed yesterday or PQC takes time. In fact, NIST started something like a competition 8 years ago, and they came up with new standards just a month ago. So it took 8 years just to come up with the right standards for post-quantum cryptography. So post-quantum cryptography is like another way to mitigate quantum computers, right? QKD is one way. QKD can just transfer keys from A to B. Quantum cryptography can also algorithmically, without using special hardware, transfer keys from A to B and also do digital signatures. And QKD cannot do signatures, right? We can use the keys to do stuff after we share the keys with QKD, but it's only about sharing keys. So PQC does a bit more. So no quantum computer is required to run PQC algorithms. PQC algorithms can run on conventional computers, which is good. We can utilize those algorithms in the current infrastructure, operating systems, networks, and so on. So it is easier for PQC to be integrated into the existing systems. So the people who designed algorithms, and there were many submissions, try to come up with algorithms that were based on mathematical problems, but not the usual old problems that current public key cryptography base its security on. New problems, right? And these problems are hard for both classical and quantum computers to solve. So if it's hard for both of them, then algorithms based on those problems are hard to crack by both of them. In any case, we knew we need new algorithms, because the old ones, it's like a single point of failure, because source algorithm can crack all types of algorithms that we currently use. So we need new algorithms that are based on different types of problems, because this way we have alternatives, right? If something breaks, we can use something else, some other algorithm. Now, these are the evaluation criteria for the NIST PQC effort. Those who submitted algorithms had to meet all those requirements, and we won't go through the list in detail, but you realize that everything makes sense. They have to be strong against the known attacks. They have to come up with proofs. So if you suggest an algorithm, you need to clarify what mathematical problem is it based on, and your algorithm is equivalent to this problem. So if we know this problem is hard, so if there is this equivalency proof, then we feel okay with the algorithm and so on. Um, Also, NIST came up with some other requirement, a security level. So one has to indicate the security level of all right, of the proposals. Um, so we have this is the table at the bottom right. Um, so the higher the number, the stronger the algorithm. So these algorithms have to be used in different environments, different applications. One has to choose and pick the right one for the right application. Okay, so this brings us to today. This competition took many years to complete. Last month, 3 of the algorithms became standards, and one of them is expected to become a standard by the later this year. So we do have one algorithm as a standard now for key encapsulation, key exchange, and 2 at the moment, and 3 before the end of the year for digital signatures. As you can see on the table on the top right, the algorithms right now are based on 2 different, already standardized, are based on 2 different types of problems. That's why NIST came up with, another competition-like approach and asks for more submissions. Right? So we hope to have more algorithms standardized in the next few years. One of the candidates, Psych, was a strong candidate at the beginning, but eventually a security hole was found and it got broken. So this means that even PQC algorithms who are promising can be broken, right? That was a lesson learned. So as we said, multiple algorithms will be eventually standardized for many different reasons. Okay, there are many entities that help standardize what's going on. Some national agencies like German BSI or the French ANSI made some proposals a few years back, but in the Western world, everybody follows NIST. So whatever NIST comes up, we have to more or less follow. All right, and this is like my last slide. I will share the slides with you so we can see the details further on. At the moment, what's the process for transition, right? We have to understand the standards that they recently became available. These have to become part of protocols and libraries so that everybody can use them. And the state somehow has to pressure, the community to utilize those standards one way or another. So organizations have to understand that, what are the threats, right? That we have to come up with a plan to accommodate those threats with a roadmap. We have to read the transition guidance by NIST, HC, and so on. We have to talk to vendors who we buy products from, tell them that, every time we sell something, it has to be quantum safe compatible, and educate the workforce. We're not supposed to use non-standardized PQC. All right, that was the bit about PQC. Do you have any questions?